Okay, let's look at section 10.4 continued. Let's try to prove the following theorem. Right? For any non-empty set, power set of A is numerically equivalent to 2 to the A. Right? So let's try to show that. So in order to do that, we have to come up with one-to-one onto function from the power set of A to 2 to the A. Right? So let's define it this way. So define function, let's call it the capital F, right, from the power set of A to 2 to the A by this definition. So let's say f of s, right, s is an element of the power set of A, is equal to, right, so f sub s, right, which is a function in 2 to the A, right. I have to explain what the f sub s is, so I should say where, right, f sub s is defined as, so of say A is defined as, right, 0 if A is not in S, right, and 1 if A is in S, right. So this is a definition, and we wish to show that this capital F is a bijection, a bijective function from the power set of A to 2 to the A, right? So let's try to show that it's one-to-one. So number one, right, let's try to show that capital F is 1-to-1. Right? So let's do that. All right, first, let's start with f of s1 equals f of s2, right? So this is just a given, right? Then what we need to do is we have to show that s1 is equal to s2. So the s1 and s2 are the same set, all right? So by definition, we know that f sub s1 is equal to f sub s2, right? So this is coming from 1 and also the definition up here. So this is just the definition. All right. What does that mean, right? So we have to show that S1 is equal to S2. So I'm going to do an element chasing, right? So we're going to do choose any element, say A, in S1, right? So that would be S1. So that would be a given, right? And I'm going to try to show that the A also belongs to S2, right? So let's do that. So it's 4, right? So we know that since A it belongs to S1, F sub S1 of A, right? Since A belongs to that set, so it's going to be 1, right? And also you have f of s1 and f sub s2 are the same, So you're going to have exactly the same value, f sub s2 of a, right? So I'm using, of course, 3. And so using the fact that not line number 2, right? And of course, I'm using this definition up here, so it's going to be a definition, right? All right, so which means that f sub s2 of a is equal to 1, which means that s belongs to s2, right? So it's 5, right? So a is in s2, right? So I'm using 4, right? And of course definition, right? Since it gives you 1, which means that the element has to belong to that set. So I'm using definition again, right? So this will show that the 6, right? Therefore, we could at least show that the S1 is a subset of S2, right? So I'm using 3 and 5, right? And I'm going to be a little bit lazy here. Since S1 and S2, the condition is all interchangeable, so I'll just say 7. We can also get the other containment, S2 is a subset of S1, right, by symmetric argument. Symmetric argument. All right, then you have 8. Combining 6 and 7, we know that S1 is the same set as S2, right? So I'm combining 6 and 7, right? And I'm running out of room, so I'm going to say line number 9, right? So therefore, all right, since we show that start with f of s1 equals to capital F of s2, so 1, and end up showing that s1 equals s2. So I'm using 8 to conclude that f is indeed 1, 2, 1. All right, so we have that. All right, next we need to show that the f is onto. All right, let's do that. Okay, I'm gonna go down here. Let's show that capital F is indeed onto. Right, so let's do that. All right, so number 2, we need to show that capital F is onto. Right. Right, so let's start with so line number 1. Right, so we need to pick choose any function, say f, from 2 to the a. Right, so pick a function, so that's going to be our given, right, and 2. Right, so we have to find an element in the power set of A such that the capital F of that set actually goes to this F right there. Right, so I'm going to define this set, so I'm going to let set S to be, right, so this is just a collection of elements in A such that this F of A is equal to 1, right? So this is just definition. All right, define that. All right, and we try to claim that capital F of this particular set S is going to give you exactly the same as F. All right, so 3. All right, let's plug in this S into the capital F. So we know that the F of S is going to be, by definition, F sub S. All right, so this is just using the definition. So I'm using 2 and the definition. All right, so we have to show that F sub S is equal to this F right there. All right, so 4. So in order to show that the two functions are the same, we have to make sure that we just plug in any A, it agree with each other. They agree with each other. So I'm going to say choose any element A in A. Right? So this is just a given. Right? Then 5. Right? I'm going to list 2 possibilities. If you plug in A into a function, one possibility would be f of A, so this is case 1, and turns out to be 0. Or f of A turns out to be 1. Right? There are only 2 cases. Right? So this is just all cases, all possible cases. All right, so let's look at the first case, 6. All right, assume that if you assume that f of this particular A happens to be 0, right? So I'm just looking at the case 1, right? 7, right? If f of A equal to 0, which means that A does not belong to S. So A does not belong to S, right? So I'm just using the definition. So it's a 6 and 2, 2 and 6, maybe I should say. So line number 2 combined with line number 6, right? So we know that 8, right? If you look at f sub s of A is going to be, right? Since the A is not in S, so this is going to be equal to 0, right? Right, which means that f of A, which is 0, at the same time, f sub s of A is equal to 0. So f and f sub s agree with each other for case 1. Right, so this is line number 7. And this is just by definition of f sub s. Right? And 9. All right, let's look at the other case. Right? What if f of A, so assume that f of A happens to be 1, right? So this is our case number 2, right? So 10, right? So if f of A equals to 1, then A belongs to that set. So A is in S, right? So I'm using the definition of set S, and using the fact that the f of A is 1. All right, so then 11, if A is in S, by definition, f sub s of A is equal to 1. Right, so I'm using the fact that A is in S, then of course the definition. We have that. All right, so in case 2, f and f sub s also agree with each other. All right, so that's the all the cases. So 12. Now we know that f of s, which is exactly the same thing as f, which is capital F of S, right? So this will establish that, let's say, so we have, using fact that, let's say, assume 0, so I'm using 6, and 8, maybe I should say 6 through 11, right? Show that this is that, right? So this means 13, right? We know that therefore F is onto, right? So this is number 12, and of course 1, right? So that means that F is onto, because we pick any function from 2 to the A, we could find a set such that the F of S is equal to F. So this is onto, right? So therefore, the main conclusion would be, so hence, right, since we found a bijection between the set power set of A and the 2 to the A, right? Therefore, they have the same cardinality. All right, that's it. I hope that this was clear.